On July 24, 1943, the U.S. submarine Tinosa located a massive prize in the waters west of Truk. It was the Tonan Maru, a 19,000-ton Japanese oil tanker. It was a sitting duck. The submarine commander, Dan Daspit, was a meticulous professional. He maneuvered his submarine into the perfect firing position. He was so close he could see the rivets on the tanker's hull. He fired 4 torpedoes. Boom, 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 boom. All 4 hit the target. The crew waited for the massive explosions that would tear the ship apart. Instead, they heard 4 dull metallic clangs. The torpedoes had hit the hull and simply bounced off. Commander Daspit could not believe it. He reloaded. He checked his angles. He fired again and again. In total, he fired 15 Mark 14 torpedoes at a stationary target. 13 of them were confirmed hits. Not a single one detonated. He saved the 16th torpedo, the last one in the tube, and brought it back to Pearl Harbor. He marched into the admiral's office and essentially said, "The weapon is garbage." This incident exposes the greatest engineering scandal in the history of the U.S. Navy. For the first 2 years of World War II, American submarines went into battle with a weapon that had a failure rate of nearly 70%. It wasn't the enemy destroying U.S. submarines, it was the Bureau of Ordnance in Washington, D.C. Today, we are going to autopsy the Mark 14 torpedo. We will analyze how a weapon that cost as much as a fighter plane was deployed without proper testing. We will look at the 3 separate catastrophic mechanical flaws that were hidden by bureaucracy, and how the arrogance of engineers in a laboratory cost the lives of thousands of sailors in the Pacific. To understand the magnitude of this failure, we first need to look at the economics and the ego behind the weapon. The Mark 14 was not just a torpedo, it was supposed to be a wonder weapon. Developed in the Great Depression, it was the pride of the Naval Torpedo Station in Newport, Rhode Island. In 1940, a single Mark 14 torpedo cost $10,000. Adjusted for inflation in 2025, that is roughly $220,000 per shot. For comparison, a modern Tomahawk cruise missile costs about $2 million. But in the context of the 1940s economy, firing a Mark 14 was like firing a Rolls-Royce at the enemy. It was expensive, complex, and treated like a holy relic by the Navy brass. The engineers who built it were so confident in their design that they made a fatal mistake. They never actually tested it with a live warhead against a real target. Why? Because the torpedoes were too expensive to destroy in tests. They ran simulations. They ran calculations. They fired dummy torpedoes with exercise heads that were designed to float after impact so they could be recovered and polished. This created a laboratory bias. The weapon worked perfectly in the calm waters of Narragansett Bay during peacetime. But war is not a laboratory. When the war started in December 1941, U.S. submarine captains immediately reported problems. They would fire at a Japanese cruiser, hear the torpedo run, see the wake pass right under the ship, and nothing. This brings us to mechanical failure number 1. The depth control. A torpedo is essentially a mini-submarine. It has a sensor that measures water pressure to determine its depth. If you set it to run at 10 feet, it should run at 10 feet. But the captains reported that the torpedoes were running too deep, passing harmlessly under the keels of Japanese ships. They sent furious reports to Washington. The Bureau of Ordnance, led by Admiral Ralph Christie, fired back a memo that essentially said, "The torpedo is perfect. The problem is your aim. You are firing them wrong." It took a rebel admiral named Charles Lockwood to prove them wrong. Lockwood didn't trust the Bureau. In Australia, he took a fishing net and strung it across a bay. He fired a Mark 14 through the net. The torpedo broke the net 25 feet below the surface, even though it was set for 10 feet. The engineering error was embarrassingly simple. The Bureau had calibrated the depth sensors using dummy warheads filled with water. But the live warheads were filled with TNT. TNT is lighter than water. The center of gravity shifted. The nose of the heavy torpedo tended to droop, causing it to dive deeper than the sensor realized. The perfect weapon was running 11 feet too deep because the engineers forgot to account for the density difference between water and explosives. And they fixed the depth setting, the captains expected to start sinking ships. But the nightmare was just beginning. Now that the torpedoes were actually hitting the ships, they were exploding too early. This was mechanical failure number 2, the magnetic exploder. The Mark 14 was equipped with a secret device called the Mark 6 magnetic exploder. The theory was brilliant. You didn't need to hit the ship directly. You could fire the torpedo to run under the ship. The exploder would sense the massive magnetic field of the steel hull and detonate the warhead directly beneath the keel. An explosion under the keel is devastating. It creates a gas bubble that lifts the ship out of the water and snaps its back. It is far more lethal than a hole in the side. But there was a problem. The Earth has a magnetic field. The engineers designed and tested the exploder in Rhode Island, which is in the northern hemisphere. The Pacific War was fought near the Equator. As you move closer to the equator, the Earth's magnetic flux changes. The delicate sensors in the Mark 14 were not calibrated for the magnetic variation of the South Pacific. The result was premature detonation. The torpedo would approach a Japanese destroyer, sense a slight change in magnetism, or even just a wave, and explode 50 yards away from the target. The Japanese captain would see the explosion, realize he was under attack, and drop depth charges on the American submarine. The wonder weapon was acting like a giant alarm bell, alerting the enemy to the submarine's location. Admiral Lockwood demanded the magnetic exploders be disabled. The Bureau of Ordnance refused. They had spent millions developing this secret tech. They argued that the captains were just making excuses for poor performance. It took nearly 2 years of bureaucratic warfare before Lockwood officially ordered his men to deactivate the magnetic sensors. So, they fixed the depth. They disabled the magnetic exploder. Now, finally, all the submariners had to do was ram the torpedo directly into the side of a Japanese ship. Simple, reliable contact detonation. That leads us to the Tinosa incident I described at the start. This was mechanical failure number 3, the contact pin. This is the most paradoxical failure of them all. The Mark 14 had a firing pin mechanism located in the nose. When the torpedo hit a ship, the impact would drive the pin backward into the primer, triggering the explosion. Commander Daspit on the Tinosa had fired at a 90-degree angle, a perfect, perpendicular shot. This should have been a guaranteed kill. Instead, it was a dud. Admiral Lockwood was furious. He took the torpedoes brought back by Daspit and decided to do what the Bureau refused to do, real-world testing. He didn't have a laboratory. He had a crane and a cliff in Hawaii. They hoisted live torpedo warheads up a 90-foot crane and dropped them onto a steel plate to simulate a high-speed impact. When they dropped the warhead flat simulating a perfect 90-degree hit, it didn't explode. When they dropped it at a weird angle, glancing off the plate, it exploded. The engineering flaw was in the guide rails of the firing pin. The friction on the rails was too high. When the torpedo hit a steel hull at 46 knots, about 50 miles per hour, the deceleration forces were massive. The firing pin was heavy. The impact caused the guide rails to distort and pinch the pin. Basically, if you hit the target too perfectly, the force of the impact jammed the firing mechanism before it could touch the primer. The torpedo crushed its own nose without detonating. This meant that for 2 years, the best submarine captains, the ones who maneuvered for the perfect 90-degree shot, were the ones getting the most duds. The bad shots that hit at glancing angles actually worked better. It was a cruel joke. The better you were at your job, the more likely your weapon would fail you. The cost of this scandal cannot be measured just in dollars, although the wasted ordnance was in the millions. The real cost was in time and tonnage. In 1942 and 1943, the U.S. submarine force was the only branch of the military capable of striking Japan directly. If the Mark 14 had worked properly from day one, maritime historians estimate that the Japanese merchant marine would have been decimated 6 to 8 months earlier. Millions of tons of supplies, oil, rubber, steel, reached Japan because American torpedoes were bouncing off the hulls of the ships carrying them. It also cost lives. Submarine warfare is a game of stealth. You usually get one shot. If that shot reveals your position without sinking the destroyer hunting you, you are dead. How many U.S. submarines are on eternal patrol at the bottom of the Pacific because their torpedoes exploded prematurely or failed to stop a charging destroyer? We will never know the exact number, but it is certainly not 0. The solution came late in 1943. The Navy finally redesigned the firing pin, lightening it and changing the materials to reduce friction. They threw out the magnetic exploders. They recalibrated the depth settings. By 1944, the Mark 14, now effectively a dumb, simple contact torpedo, became the most devastating weapon in the Pacific. It strangled the Japanese Empire. US submarines eventually sank 55% of all Japanese naval tonnage and destroyed their merchant fleet. But they did it in spite of their weapon, not because of it. The lesson of the Mark 14 is a lesson in the dangers of the sunk cost fallacy and bureaucratic arrogance. The Bureau of Ordnance was so invested in the idea that their expensive, complex machine was perfect that they refused to look at the data coming from the field. They trusted their blueprints more than they trusted the men pulling the trigger. It is a pattern we see in engineering history repeatedly. The Tiger tank was too complex for the mud, the B-29 engines were too advanced for the heat, and the Mark 14 torpedo was too smart to actually explode. In war, complexity is seductive, but simplicity is lethal. A $220,000 torpedo that doesn't explode is just an expensive piece of pipe. A $500 mine that works every time is a strategic asset. So, here is the question for the comments section. If you were Admiral Lockwood in 1942, would you have violated orders earlier to disable the magnetic exploders, risking a court-martial to save your crews? Or does the chain of command exist for a reason, even when the technology is broken? Let me know your thoughts below. And if you want to see another example of American industrial might overcoming engineering failure, check out our video on the Liberty ships. The vessels that were built faster than the U-boats could sink them, but occasionally snapped in half in cold water.